again, I should thank the organizer for this nice conference. So yeah, there is a huge, I think, noise in artificial intelligence and how to use machine learning for doing some modelization. So what I'm going to present today, I should be very short and brief. So I just wanted to show you something we do in the numerical modeling of some problems we're dealing with. As I said, I have changed slightly my talk just to talk about something we have just started yet, and where we seek your advice and also your comment on what we're going to do. So I'm going to talk about something, a project which is just get funded, I think a couple of weeks ago. And this project is about something to do with try to model and the impact of the oceanic circulation on the resource, fish mainly. And this is a project which just, as I said, gets funded by the call by CNRST and OCP and also UM6P. And our partner is the NRH, where we are going to collaborate with them and get some models to work for these resources. And yeah, so this is a project for 3 years, and the budget is about, well, above 2 million dirhams for this period. So what the plan would be for this project is to try to look at the impact of the recirculation oceanic on the fish, mainly sardines and anchovies, and see what we can do in terms of using some machine learning techniques and also some modelization and hybrid these two, and come up with a model which tells us where we can optimize these resources, where we can find them, and also how to do smart fishing. So if you see these pictures here, or these animations, just telling you how these fishes, mainly these are sardines and anchovies, and these how they behave. And most of the time, people, they work on this population or dynamics of population. They just take the look at how they behave on when a predator or some other stuff happen there. But there is a few works, they can tell us the impact of the recirculation on these mass of fishes. And what we want to do is to try to quantify, or maybe qualify as well, the impact of the water, mainly recirculation in the ocean, and look at the impact on these fishes, and also to find the places when and where we can go and fish, well, intelligently. That's the word maybe we can use for this type of fish. And what you see here, this recirculation of the fish is nothing to do, just the impact of the water on them. It's no predator there, is nothing there, but this mainly driven by the oceanography. And nowadays, this change in climate, and that changes the temperature on the ocean and the salinity as well. And this will may change also the way how we do fishing today. So that's the idea, is to look at how the impact of the ocean or the circulation on the fishes, regardless whether there is predators or there is food or not. Okay, so we do know many things how to model this stuff. So these some exercise can a student at level 4 or master student can do that. This is CFD or color for fluid dynamics. And these are just the dynamics of a fish. This could be a particle. I would call it particle now. And once they start to vibrate or to move, we can generate, or well, we can generate a mesh and then do nice numerical modeling and come up with these vortices, which are mainly released when these small fish start to move. And you can see those share vortex there and etc. So we do know how to do these type of simulations, but this is not what we want to do in this project. In this project, we want to see the reverse. So we want to see the impact of the water on the fish, not the fish on the water. So this thing here just telling you if a particle or a fish vibrate based on some movement or some linear elasticity or plasticity there. So how the water or the recirculation will be altered. That's the exercise here. But that's something we don't want to do. And again, this is something also can be done by just considering this is a shark, obviously, and when it starts to vibrate or to move, it generates these vortices, and the shear or the friction there, you can calculate the lift or the drag forces, etc. So that's something we can do very easily, but that's not our purpose. So we want to see how the water or the ocean recirculation will affect the movement or the dynamic of those fishes. And again, that's something maybe should be considered when you do machine learning or artificial intelligence, because we do know a lot about behavior of sardines and anchovies, and that data could be used to develop some tools for deep learning and then use them as supplement or complement as well on the numerical modeling we are doing. So this is mainly what I'm talking about today. And so the objective in all our work is to try to develop some numerical models to do this modeling step. But nowadays, there's a lot of noise and people started to move to machine learning. But some of these extreme idea, they are talking about, well, just discard all the modeling and focus on the machine learning, because we do have access to a lot of data, and that data could be used as a tools for modeling or doing the predictions for the coming days or coming years. However, that's not enough for this type of projects, because even if you have data, you still need to do some modeling to be able either to improve the quality of this data, or to use the data to calibrate and validate the modeling part you're doing. So now, why this is useful? First of all, we can track the fish masses in the sea. So that's the idea of this project, is to try to come up with time and space maps. They can tell us where we can, when and where we can fish, based on that outcome coming from the hybrid modeling and the machine learning. So that's something, the plan, and also to develop an efficient way for fishing, and that's something we call smart fishery. And smart means you can incorporate some in situ and also real life or time decisions. So that's what we mean by smart, that you don't destroy the resources quickly and massively. The other thing is the possibility to identify the areas where we can, when we expect to have high resources, again, based on that oceanography recirculation. And that's something we call it the funny name of Operation Marhaba. And that when the immigrant from Europe, they started to return to Morocco, and that's something maybe could be also done for the fish. So there is places and locations and also times when we can do these nice or massive fishing. So, and for our client, and in this case, our NRH institution, so we try to reduce the cost and also to look at the impact of climate change on these resources, especially in the north of Morocco. So the plan is to focus in Larash and Mehdia locations and try to implement all what we're going to develop on those areas, which NRH has a lot of data. Okay, so how are we going to do that? So that's the business we have been doing for ages now, it's about 20 years now. So we develop mathematical models, and in this case, we need mathematical models for the oceanic circulation and also for fish dynamics. I should say here, we're not doing those ordinary differential equation to do the population of fish. That's something now is history, and we're trying to put more advanced models there with some stochasticity as well. So in that case, if you want to do that, so you can have many models, you can pick one of them based on what you're going to model and how you're going to model and how much price you want to pay for. So there's some models which are very expensive, and some model. I'm talking about the difficulty and the complexity of these equations and the prices that complexity in the models. And then at this stage here, we will need artificial intelligence and also machine learning. So that's needed there. At least we can use those techniques to first of all perform uncertainty quantification and sensitivity analysis, because most of these models, they involve very huge parameters, and some of them are hyperparameters there, and machine learning will help us to identify or to calibrate those parameters and find the best or the optimal ones to put in the model. Once the model is established, and then we can move to the next stage, which will be developing numerical method and computational tools to solve those bunch of partial differential equations, stochastic differential equations, and also some fractional differential equations for mainly fish dynamics. And then we can choose based on the price we want to pay again, which model or which method we're going to use. And I will tell you later which one we're going to put in this project. And again, I should emphasize here that we still need to switch that machinery of artificial intelligence and also machine learning here, because those numerical methods, they require data, and that data could be coming from a trained algorithm that will take in data in real life time and then calibrate the model. And some of the stuff there could be, I think, done directly or using just the machine learning or artificial intelligence. Okay, good. So let me quickly show you what we do for the modeling oceanographic, and then quickly go through the models and show you some preliminary results. And because of the talk supposed to touch on the machine learning applied to sediment transport, I didn't want to repeat what I have already presented maybe 2 years ago at Mehdia. So I will show you some results we got with some PhD students on using machine learning for sediment transport. Okay, so what we do here, so we solve partial differential equations. So that's the model for the oceanic recirculation. And as you see that, if you have done PDEs, that's something straightforward. If not, those are just the physical laws. First of all, the conservation of mass and then conservation of momentum. And you see these are the velocities in the 3 dimensions, u, v, w, and here the pressure there, which is supposed to be also hydrostatic. In our case, you have a density. In this case, this is not true because the density on the ocean will not be constant because it will depend on the pressure, the temperature, and the salinity as well. So it should be a nonlinear term here. Also, the viscosity here must be turbulent, and then you have a lot of terms here involving parameters, and those parameters need machine learning. So that I think that's the place where machine learning can tell us too much about which parameter to use, when and where. That's the idea. So you have the Coriolis term here. You're supposed to have a friction term, wind terms, and also interaction between the dynamics of fish and water, and then you get some extra reaction term here for temperature, salinity, and also some variation in the density as well. So those terms, I don't want to bother you with them, but believe me, those terms are very huge and large. They're involving many parameters. Okay, conservation of momentum in the x direction, momentum in the y direction, and momentum in the z direction. Of course, we will add conservation of energy, and that case would be the change in the temperature and salinity as well. So that's basically what the equations look like. However, the characteristics for water is different than other fluids. So we have to deal with hydrostatic pressure. And in this case, if you do that, so the variation of the pressure at the vertical direction will be dealt with just integrating that equation, and then you replace the pressure with this term here, and for that you get this zeta or xi, whatever call it here. So that zeta here will be the free surface, and that's what makes these problems challenging, because you will be dealing with a domain where the surface is moving. So that means at every time the domain changes, and for that you might need to remesh at every time step you do that. But that's something we're not going to do. We will do multi-layer shallow water stuff, and that's something we have been doing also for the past couple of years. Good. So if you do that, you need still to add data, and the data should be mainly related to some currents. So you will have Ekman currents, and that's the basic equation for that. So that tells you how the water or those currents will be affecting the mass or the particles you will be injecting on the ocean. And again, you will see there is some other parameters there, and those parameters, they need calibration here. So that's those magic number you see there. So you need calibration. That's what we use, but this is supposed to be changed from one location to another, and maybe changing with the time as well. But those are the main I think empirical equations used in the literature to model Ekman currents. And again, as I said, this is something we might need some machine learning, especially to calibrate those parameters involved there, and based on the data provided by remote sensoring or by just the NRH, our partner. They have I think, equipment to measure these type of parameters or those currents there. Okay, once the Ekman currents are done, so you move to the geostrophic current, and that case also we have these equations there. It should be other terms here, just to show you the complexity of these terms there. So we need to integrate these parameters on the phi here, just latitude in degrees, and where we need also to account for the Coriolis forces, which depend on the rotation of the Earth, of course, and that's something also need to be included in the model. Good. So assume you have done for all that for the water flow, you end up with a field where you have your velocities, pressure, density, etc. So anything you need for the recirculation of the ocean, so it will be provided. You store that data, and then you need to inject those particles or those fish. And again, this is the way how, or the simple way how you're going to do that. So suppose these X, Y, Z are the position of a fish, and that will be driven by some drift and diffusion term, and that's the term related to the recirculation oceanic. And you see here that the flow velocities UVW, and this includes the water flow plus the Ekman plus the geostrophic flow velocities. And then you have a dispersion matrix there. This is supposed to be a tensor there, and that will tell you just how, or the probability of the fish to move in one direction to the other. And then you have some stochasticity inside, because that's something one need to account for, because when we talk about artificial or this intelligence, we need to think about intelligence of the fish, because that intelligence is different than the way we do things, and that allow us to include these stochastic terms there. Those are just Brownian motion, and you have this quantity that tells you that's the variation of how much stochasticity you're gonna add to your system. Yeah, so this is still a simple way. So it should be more complicated than this one, because this Brownian motion, or this will generate some white noise, and it should be correlated, of course, and that will be a more nonlinear system to be solved. And again, this is where machine learning can do a very good job, especially when you train your machine to allocate which Brownian motion to use for those for each fish on your system. So if you write that in a compact form, so you end up with a huge system where you have could be a big matrix here, and that's the tensor of the dispersion. In our case, we have a 3D model. In that case, you will have these turbulent dispersion here, and then you have this longitudinal dispersion. And again, I'm giving you here some magic number, but this is something also machine learning, we need to do that to calibrate which parameters to use for this coefficient. And you have also another coefficient here. So that's, if you look at the number of the parameters involved in this modeling part, they are very huge. And to find those parameters which are relevant for dynamics is also very difficult task. And also the correlation between these parameters in the system is highly correlated, and you cannot discard one term to the other. And that means it's very hard to find these hyperparameters in your model. that's something I think machine learning could be a very, very good direction to go and do that. Okay, so what we do for, I'm not going to go into details on these techniques because each of these techniques need an entire section for that. And this is why I said this supposed to be just a chat rather than a conference. I just want to chat with you on these issues here and to go through these in details. Each of these steps here need an entire lecture or conference. So what we do in our case, or what we're planning to do, so to use a finite difference discretization for the vertical coordinate, so that means you end up with a superposed 2D models, but they are connected to each other, of course. And then you have like a multi-layered model, and you solve it in the plane XY, but they are superposed with some coupling conditions. So then you solve this multi-layer thing for using some finite volume. Why finite volume? I will tell you later, not finite element. And then impose some exchange terms from one layer to another. Then update the free surface. Then add the Ekman and the geostrophic currents to that flow velocities you get from your finite volume method. You store all the data. And then at this place here where machine learning and the training would be very good to enrich the outcome, or especially the predictions. So in that case, we will store the data coming from the simulations, and also we have data from the field. And these, I think this step here, when we do the dispersion, we will use those techniques there and then come up with predictions. Quickly, what the finite volume is doing. So if you have a conservation law here, that's a simple conservation law where you have your quantities here, could be density, velocity, temperature, salinity, etc. And then you have some nonlinear fluxes. So what we do in the finite volume, so we discretize the domain using nice triangulation, or could be any type of volumes, and then you integrate along this volume here. So if you do that, so you integrate this equation on the volume, and then use that green Ongo's theorem, and then this integral over the volume for this term would be just a line integral if you are dealing with 2D, and these are just the fluxes multiplied by n. So if I go back here, so what we do, so this flux at this volume would be just the sum of the flux evaluated at this h here times the multiplied by the normal here, and then the same and the same there. So that's what we do here. So that will be your finite volume scheme. So it would be just this integral over the whole volume will be just the sum, and then you have these fluxes there. And then we assume in the final volume, we have a piecewise constant solution. Each volume, the solution is constant. And the reason why we do in finite volume, because in this project, we want to conserve the number of fish, or the mass of the fish. Finite element, in most cases, in general, they are not conservative. So, and therefore, we will lose if you start with 10,000 tons of fish. You run these simulations, you end up with maybe less than that mass. And finite volume by reconstruction is conservative. So now all the finite volume schemes or methods, they look like this form here. The only difference is how you calculate these fluxes at the age. And if you look back here, so we have piece with constant solution, and suppose you are sitting on this edge here, so you have a constant solution here and a constant solution there, but you need to evaluate the flux at this point here. So what you end up with something we call the Riemann problem. The Riemann problem would be just this. So you will have discontinuity on the solution, and each volume has a different solution. Again, I'm interested to do some machine learning here to solve this. So you train your machine based on the data, so you have many solutions, and your computer or your algorithm will choose the best one. That's something people now they are thinking of to do. So for some problem, we can solve this Riemann problem analytically. So for example, gas dynamics, shallow water, so these papers where they can solve this analytically. But in most cases, and especially for the problems we're dealing with, it's very hard. It's impossible to solve them analytically. So you need to do some approximation. And also there is a zoo in the literature how to approximate that. And there may be one good thing about machine learning to pick up the right flux for the right problem you're dealing with. Okay. Good. So, but what's the problem in the final volume is we are not dealing with, if you look at earlier, so we have this flux. This flux has nothing to do with the Laplacian or the gradient, has no contribution for the gradient. And the biggest problem we will have, especially in this type of problems, you will need to integrate or to approximate a gradient. And that's very hard in finite volume, not like in finite element. Finite element is done for this type of problems, and there is no difficulties there. However, for finite volume is not trivial, is not straightforward at all, and you need to do some extra work. So what we do here, if I go back there, so we generate a dual, or we call it also some control volumes or diamond shape. So those lines there, so we will have 3 different meshes in the same platform. So this is ridiculous, as you see, but that's the way how you do the reconstruction for the gradient. Otherwise, your solution would be won't be positive, won't be satisfying the maximum or the principle of maximum. So those triangle you see there, so the black one, those they use for the normal fluxes. Those blue, the diamond there, those they are used for the discretization of the Laplacian or the gradient. And the other diamond you see there also needed for our adaptivity. So that's exactly what we do. So for each of these triangulation, we do this control or the reconstruction, and our gradient will be, or the Laplacian will be approximated on this volume here rather than this cell here. So this is why we call it cell vertex reconstruction. For each of these vertex here, we will have a control or a solution for the Laplacian. The reason why we do that, so that's exactly what we, so because we will be dealing with interaction between a water fluid and then a movement of a fish or particle or anything there, which you can model using elasticity, some nice constitutive laws there. But when the deformation starts to be large, will alter all these mesh there. So this is just to show you we are using different control volumes for the water and then for the structure or the fish here. And we managed to get a very good coupling between these two there. So that's the idea of this work. The other thing finite volume will offer you is how to do the mesh adaptivity, because we will be dealing with a very detailed structures and features for the flow. And to capture that, you still need to do some adaptivity. And that's what we do. This is a recent work which I did with a colleague in Heriot Watt and another one in Japan. And the idea is to see the impact of the wave solving this type of waves. And that's something very new. Nobody has done it before, solving these type of equations using finite volume thing. And as you see, you will get similar structure as the one you get from finite element. So you get mass stiffness metrics and also some source term here when you discretize this. And then you decide, because the wave is only acting on these two propagating fronts, there's nothing happening in between. So it will be crazy if you refine all this. But you see, once the wave hits this structure there, it's reflected, and you have a very small waves. And those waves are very hard to capture if you don't do adaptivity, or if you don't refine the mesh. And the refining we have done, we just use this multi-level thing we have done ages ago. So you just decide on some error estimator. In this case, this form could be any other one. And then you decide, you mark your elements, which one you're going to refine, which one not. And that's the idea how we done it. And again, this can be done using some nice machine learning stuff. So that's something I started with a PhD student. And the idea is to do many solutions, generate a big, huge set of data from these simulations, and then through the model in the bin, and focus only on the machine learning and see whether your machine learning or your algorithm will localize these features, and without any solving, without any modeling or any final volume discretization. That's the idea we are going to do. Good. So let me be quick. Nabil, you should stop me whenever I'm talking too much. Okay. So yeah. So what we have done for this case, we have data. These are the resource of the data. So that's something depend on which area you're dealing with. So these are the sources for these data.
5 minutes.
How much?
5 minutes.
5.
Yes.
Okay. So quickly, so this is the data we have. So, but in our case, we will need a huge set of data, and that big data also can be used for training the machine. So that's how it looks like. This is, I think, from 2019, and this is the magnitude and also the frequency for those currents there, and these are different sources for the data. You see here, there's a peak there, and this is for 365 days, is 1 year. We have a huge data, and that could be used also for training the algorithm. Good. I'm not going to talk about this because it's 5 minutes. So let me show you what we have done for the Mediterranean Sea, and this is again something we know how to solve these type of problems. These are the vortices, this is a satellite image, and then we using the simulation, we will get something that looks similar. And that's I think the same pattern there. We use the data from 2012, 2013, and then you see something that works perfectly. So that's the mesh generator there. So this is a PhD thesis of a student who is working at Ben Green now. And yeah, so we did the dispersion and the Mediterranean Sea. So sediment transport equations are tedious. It's far complicated than the ones I just showed you there. So they involve a lot of parameters. So what the student is doing, so we had some data from the laboratory here at Durham, and we run different dam break situations and also look at to the sediment parameters and get that data. And then you decide on some trade decision. And those are the four that mainly this is something you will do to train your machine. And in our case, what the student did, so just this is how you make the decision. This is the water height, and then you have some parameters there, and then you decide on the velocity, on the diameter, and other. So you have plenty of the parameters, and you need to come up with a decision which one you're going to do. And also finding the hyper parameters in sediment transport is very complicated, because if you look at the amount of parameters involved on those equations, they are really ridiculous. So you need to come up with few of them to do your sensitivity analysis or your uncertainty quantification. So what the student did, so mainly did the neural network, and also did some random forest thing on how you decide which data or which part of the data will be used for training, which part of the data will be used for testing and validation. So that's what the student did. So that's the sediment transport, and this is mainly done also in the lab. So this is just a dam break, and then you have sand here, and because of that shear stresses, you know the critical value there. So you see this erosion there. We can measure how much sand we will get, and also how deep we can go. This is only one sand, and this is 3 layers there, and you can see the amount of the erosion is different from one to another. And then you have that hydraulic jump there, and these all features we can do using finite or also some machine learning. So that's the results the student got. So this is using a random forest again. So you have lab data, and then you have some field data, and then you just look at the correlation between the sediment diameter and also the velocity of the flow, and you can see there is some high correlation there. But again, working with lab data will be completely different than working with field data. And generating lab data is very easy, but field data sometimes is very hard, and it got a lot of inconsistency there. Okay, let's move quickly. So that's what the student also did when he tried to find the correlation between the flow velocity and the water height and the concentration of the sediment. You see, those are data, and this is just a regression analysis to fit the data there, but using some nice machine learning tools. And again, this is just the errors when you do that based on the diameter of the grains or the particles in your sediment transport problem, or in the velocity, and you see how localized those errors there based on both data from the field and data from the lab. This is exactly the same like before, but again, if you look at the result we got, and this is very impressive. So if you look at this graph here, that's the bed, that's the erosion. Initially was flat, that's the dashed line there, and that's what you get using a very known model. So that's the Van Rij, which may be the most famous work done developing the empirical equation. And those cross there, that's the measurement, the data. And this is from the lab. So that's the water profile. You see a very nice hydraulic jump here. And what you see here, so the machine learning, this is solving nothing, just doing machine learning, data, data, and data. And you see that blue line there, so that's the machine learning, and that's the model solving tedious equations, and that's the data for this experiment. And the result doesn't look bad. So they are really impressive here. So similarly here, so you still look at the machine learning data you get from just machine, and the results, they look okay. So the conclusion from this example, you can still do very nice modeling and simulation without using any models, any discretizations, any finite element or finite volume or finite difference or whatever. And you still get very nice results just by training your machine and do some algorithm there. Stop here. So that's the conclusions. Yes, we can do a lot of things with equations, partial differential equations, and also with some finite volume or numerical tools, but still hybrid or coupling machine learning and numerical model could be a very interesting path to go through. But also we need still to do a lot of things, and especially for this project we are started now, and much more work has to be done. I think we are looking for students because the project is for 3 years and we have funding for 3 students to work on this project, and it should be not only engineering from Al-Hassaniya and Mohammediya, but we still need some computer scientists and also some mathematicians to do nice work on this. And thank you.